evening. Let's see untitled examples for the Bode part that we made in the last class. So in this problem, it states to plot the Bode diagram and to obtain the gain and phase crossover frequencies. So the given transfer function is 10 by s to the 1 plus 0.4 is the 1 plus 0.1 s. Again, like the last problem, the given transfer function is in the standard form or the Bode form or the time constant form. Hence, you can easily substitute s as j omega. Hence, our sinusoidal transfer function g of j omega becomes 10 by j omega into 1 plus j.4 omega into 1 plus j.1 omega. Again, this question has three terms, and the first term, as you can see, is a integral term. In the previous question we had a derivative term and k was given and we substituted k is equal to 1. Here an open loop gain of 10 is given and we have an integral term. So the first term that we will combinedly take will be 10 by j omega followed by the first order factors in the denominator. So once we calculate the corner frequencies, we get as 1 by 0.4 to 2.5 radians per second and 1 by 0.1 is 10 radians per second. So these three terms are listed in table 1 and it is listed in the increasing order of corner frequencies. So the first term is going to be 10 by j omega, which does not have any corner frequency, and being an integral term, it is going to give a slope of minus 20 decibel per decade. The second term is 1 by 1 plus j.4 omega, which has a corner frequency of 2.5 radians per second, and again the slope is minus 20. So the change in slope becomes minus 20 plus minus 20, so it becomes minus 40. The last term is 1 by 1 plus j.1 omega and the corner frequency is 10 radians per second. It again has a slope of minus 20. So the change in slope is going to be minus 40 plus minus 20, giving a total change in slope of minus 60 decibel per decade. Next, a low frequency of 0.1 radians per second and a high frequency of 50 radians per second is chosen. Again, we need to calculate the magnitude A, that is the mode of g of j omega in the decibel for these four frequencies. So at omega L and omega C1, we are going to take 20 log g of j omega, where, as I said in the previous problem, the corner frequency, the first integral term is taken, so 10 by j omega, which is our term. So omega is substituted as the lower frequency 0.1 and we get the frequency as 40 decibel. At the first corner frequency, again this is substituted and we get as 12 decibel. For the higher corner frequency and for the higher frequency omega h, we use the standard formula of gain to calculate the magnitude. So at omega c2, it is going to be the gain at omega c1 plus slope from c1 to c2 into log of c2 by c1. So as we can see, the slope change is minus 40 and minus 60. So these values are substituted here to get your respective magnitudes. So for the calculation of omega c2, it is minus 40 into log 10 by 2.5 plus the previous gain 12. So you get as minus 12 dB. And for the magnitude at omega h, you take this value minus 12 plus the change minus 16 into log 50 by 10 and you are obtaining it as minus 54 dB. So our 4 points A, B, C, D are plus 40, plus 12, minus 12 and minus 54. So these will be marked as points on the graph, and as I repeatedly said, we use a scale to join these points by a straight line. Now moving on to the phase plot, as you can see, being integral term, in the numerator you don't have this 10 is going to be 10 angle 0 degrees. So you don't have any phase contribution from the numerator, but the denominator is going to have minus 90 degrees, minus tan inverse 0.4 omega and minus tan inverse 0.1 omega. So that is the expression written here. Phi is equal to minus 90 degrees minus tan inverse 0.4 omega minus tan inverse 0.1 omega. So the phase angle is found for various frequencies and we are taking the points as E, F, G, H, I, J. So these are again plotted using the same semi-log sheet and again the y-axis, and we are going to join the points by a smooth curve or a freehand drawing. So let's see the graph. So I've taken this as point 1, so this is 1, this is 10, this is 100, 1000 and 10,000. So this is your omega in radians per second. And again, since my magnitude plot involves from minus 54 to plus 40 values, these are the dB magnitude that is chosen: 0, 10, 20, 30, 40. So A at 40 dB is your first point, B at 12 dB is your second point, C at minus 12 is your third point, and D at minus 54 is your fourth point. These are joined using the straight lines, and this gives you your magnitude plot. Similarly, the phase values are taken here, the 5 integers, and we have plotted your E, F, G, H, I, L, and it is a freehand drawing, and that gives you your phase plot. We have been asked to find out the gain crossover frequency and the phase crossover frequency. And as you remember, the gain crossover frequency is when your magnitude plot crosses the 0 dB. So as you can see, this is the 0 dB line, and this particular frequency is found to be 5 Hz. 5 because this is your 1 and this is your 10. So in this decade, 5 is going to represent your 5 radians per second. So you can see that at 0 dB, you are getting 5 radians per second. Now to find out the phase crossover frequency, we are going to consider your phase plot, and you are going to take your 180 degree line, and the 180 degree line is being marked to your phase plot, and you can see again that this also becomes 5 radians per second. So in this particular question, your omega gain, your gain crossover frequency and phase crossover frequency are one and the same, and hence your system is going to be marginally stable or limitedly stable. You can't say that your system is stable, and neither can you say it is unstable. So this system where your omega PC is equal to omega GC is known as a relatively stable or a marginally stable or a limitedly stable system.